Welcome to the next lecture. We will be actually studying mainly the authentication and data integrity. In both the cases, we have to use a class of mathematical functions which are called hash functions. So let's try to understand first what is a hash function. So here is a simple description. Hash function is something which accepts a variable length block of data m. You know the dividing the data into blocks. Already we have done this in RSA algorithm. And if you take that as an input and a hash function, or it is an algorithm which we will see very soon, it produces a fixed size hash value which is denoted by small h and is written as capital H of m. Okay, we'll see in detail what it means. Now, good hash function in some sense has a property that if the result of applying the function to a large set of inputs will produce output that are evenly distributed and apparently random. So that is, if you apply different inputs to it, you apply some m1 then m2 and m3, the output will look like random apparently. Okay, and evenly distributed means sort of a uniform distribution. Again, we will see one example what it means actually, but in general, suppose if there are n such different blocks of data which you are basically providing to hash, the probability with which you observe any particular hash output will be 1 by n. Okay, this you will see very soon. But the important property of hash function is that the output should appear to be random. So we can say in this sense, the principal object of a hash function is data integrity. So that means that we want to ensure data has not been changed by any eavesdropper or hacker. Till now we have been worried about that hacker or eavesdropper should not be able to decode, should not be able to read what was or understand what was transmitted. Now hacker may try to change the data. The purpose of hash function is, one of the main purpose is data integrity, that we should be able to ensure that data has not been changed, compromised. For that purpose, we have a class of hash functions which will be called cryptographic hash functions. They are basically an algorithm for which two conditions should be satisfied: that it should be computationally infeasible to find either a data object which maps to a specified hash function. It's called the one-way property. In other words, there should not be inverse, it should not be invertible. Okay, if you have any data object m and you find the hash of this, now given this hash function only, you should not be able to tell which m produced it. The other property is two data objects that map to the same hash. It's called collision fee probability. That is, it should not be possible that there are two different message blocks m1 and m2 such that h of m1 is equal to h of m2. Two different messages should not have same hash. These are the two important properties which are to be satisfied by a special class of hash functions which are called cryptographic hash functions, which will be used in case of data integrity and authentication, which you will see very soon. Here is a general description of cryptographic hash function. It takes input the variable length data block, which is here m. Suppose there are L bits there, and there is a this P which is actually padded with it. What is this P? P is actually about, P is inserted there which contains the information about length of this block, how many bits they are. And after applying the hash function, and it is basically shown in this way, mechanical way, so that what it infers is, you can give input and it gives output, but you can't do the reverse. If you see the structure here, if you feed something here, there are knobs here which will be closed and it will not allow you to take the output here. So it means it is not invertible. And after feeding this data block of length L bits and P, which contains the information about the length of original message in bits, both this message and this P is padded with the message block and fed to this hash algorithm. What it produces is a fixed length hash value. For example, it may be 1024 bits, which is exactly 1 kilobits. It may be that whatever be the length of the message, the output will always be fixed length. This is a general description of hash function. Now, what are the applications of hash functions? For one of the application of hash functions is it provides us a mechanism to verify the integrity of message, and this is called message authentication. So in this case, in message authentication, what we do is we use a hash function to ensure that data is received exactly as sent. Okay, so data is received exactly as sent, that is, there is no modification, no deletion, no insertion, or no replay. What is this no replay? We'll see it in detail when we will do message authentication code for using hash functions. Now, how is this achieved? Here is a very nice illustration which will describe how hash function can be used for checking the data integrity or message authentication. Now, what will be done is that the transmitter here we call Alice, or the sender. It computes the hash of some message, suppose M, which you need to be transmit, and ensure that there is no change in the data. So what you do is you transmit both this message M and the hash of this message H of M. You see here it's a data. This is the data block, and you are computing the hash of this, and now this is the data block and hash. We'll see in detail. Remember that hash is usually of much less length, smaller length than the data, and then you transmit this here. Now what Bob will do, Bob knows that the first amble of this frame is data. First bits are the data, first few bits, and then the last bits are the hash. So Bob will also compute H of whatever is received here, this data, and it will check this H is same as the hash here stored in this. If there is a mismatch either in the message or in the hash, then it means that there has been some change in the data. So intruder has changed. So in other words, we have achieved a message authentication. At least in this case, it gives a signal that your data is compromised. They immediately can communicate with each other and try to secure their data. Okay, but there is one important thing here, that the hash must be communicated in a secure fashion. If hash is not communicated in secure fashion, then adversary can also change data, and still one will not come to know that it has been changed. So what to do for that? We will use some form of key along with the hash. But before that, let's illustrate the attack which is possible even with hash, which is called man-in-the-middle attack. I again repeat here, so you may be confused what actually hash is. We'll do some examples. Right now we take hash as an algorithm which takes input as a data block, produce a fixed block of output in such a way that you cannot invert it easily. Okay, the inversion is nearly impossible. Also, if you feed two different message blocks to the same algorithm, it is almost impossible to find an algorithm in the category of hash functions which will produce the same hash. Just remember this thing right now. What actually H is, we'll see it in detail. Now let's go to this man-in-the-middle attack. And it is a pretty simple attack, and I think it's not very difficult. So suppose you have some data, let's say M. We compute hash of this data, suppose H of M. Okay, so that is stored as H, so it is here. Then you transmit this data and this M. Now Darth is your hacker sitting in the middle. That is why it's called man-in-the-middle attack. See, this H algorithm is open. Okay, it is public. It is not something which is shared between only transmitter and receiver. So Darth also knows it. Darth also knows the structure that the first part is data and the last part is hash. What will Darth do? It will change the data. Suppose you transmitted M, it will change M to M dash and compute hash of this M dash, and then transmit this altered data here. What will Bob do to authenticate the message? Bob knows that the first part is my data, suppose M dash, and computes the hash of m dash, compares this h of m dash with h, it will definitely come same, because Darth has changed the message as well as hash function. See, in this way the hash function will provide message authentication only if attacker changes only either data or hash. If attacker changes cleverly both, that is, it first changes the data, then whatever data it places, it first computes hash of that data and then embeds that, then this is a failure. So Bob will think, okay, data is not compromised, but actually data has been compromised. This attack is called man in the middle attack and is one of the famous attacks in cryptography. Now we want to overcome this disadvantage of using hash function without securing it. So there are a couple of ways to do it. One of the ways is that we will concatenate the message and hash code and then encrypt it using symmetric encryption. Okay, so you can use any symmetric encryption scheme like DES or AES. Now since only A and B are the two parties, let me first put the figure here. Okay, so what I mean by A is the transmitter side and B is the destination side, receiver side. See, this is the message M, this is the H. This operation is concatenation, that is, you combine them, M concatenated with H. Now whatever block you get here, this E is any of symmetric encryption algorithm. It can be DES, it can be even the cipher algorithm, it can be even RC4, it can be AES, whatever. It has definitely a secret key, that is the base of symmetric encryption, and you apply this encryption with key K over the concatenated, that is M concatenated with the hash of M. Now you see you have encrypted it, hence there is a confidentiality added. Hacker cannot know what it is because hacker does not know the key, but destination has the key. So destination will start the decryption algorithm. Once destination uses decryption algorithm, then it knows that the first part is M and the second part is hash, and it will compare and ensure that there is no breach in the data integrity. This is one way out. The other way out is actually very simple. Instead of encrypting the whole message and hash, we can encrypt only hash only. So let me show the diagram of that. Look at this. You have message M, okay, and you compute the hash of this message M, H of M. Encrypt only hash of the message, okay, don't encrypt both the things with some secret key. This can be any symmetric algorithm again. Then concatenate it. Now you are concatenating M with encrypted form of hash, okay. Now what you get is the first block will be M, but second will be encrypted form of hash. So hacker, suppose if hacker changes M and replace it with H of M or say M dash, what will be the result? The destination knows that I have to first decrypt the hash. When destination will try to decrypt H of M dash, it will not give you M dash. Immediately destination will come to know there has been compromise with the data integrity. Data has been changed. So this provides a good layer. And you see, this is better method because you are having less load here on the algorithm. You are not encrypting the whole data as well as hash. Hash is of smaller length than the original data block. Now is there any other way out? Okay, so there is one more way out to do this. In that case, we use little bit different thing which you have not seen till now, which is the technique of having some common secret value. Although we'll not go in details, but let me just show the block diagram of it. So the third technique assumes that there is some S which is called a secret value, which is shared between only the legitimate parties, that's the transmitter and receiver. Secret sharing is one of the topics in cryptography as well as information theory. And what secret sharing means, what does it mean really? One example I can give you, suppose if you take the case of wireless communication, so there are two parties which are communicating with each other, and the channel gain, which is usually random in nature. The value of channel gain at any point of time is a random quantity which can be shared between the transmitter receiver. And there are other ways also in computer science. They study it, what are the different ways of having secret values. But assume that there is some secret value S which only legitimate parties know, hacker doesn't know. So there is no encryption algorithm here, there is no secret key applied here. Or you can see in one way, so S is some sort of a secret key, okay, so which is being known only to transmitter receiver. Now what will it do? Now what will we do? We'll concatenate the message and this secret value, which you can think of a key also, then compute hash of this. Okay, so I will compute hash of M concatenated with S. Then this M and hash of this will be transmitted. See, the upper block contains M and the lower block contains hash of M and S, not just M. This is the key. Now if man in the middle attack is performed, that guy does not know S. So if that guy changes M and suppose M to M dash and puts H of M dash, now what will receiver do? Receiver will think that this is not hash of M dash, rather this is hash of some M concatenated with S. It will try to compute that, and when it does that, it will basically get immediately known that the message has been compromised. Okay, and then you can do one more thing, which is I think more conservative and more secure, that you can have the secret value S also. Then you can concatenate M and S and do the hash, then concatenate message and H of S concatenation M, then apply encryption algorithm to this. Okay, double security. Then receiver will first decrypt it with key K. Then receiver knows that the hash is not of M, it is of M concatenated with S, and it will accordingly compare it and it will get that whether data is compromised or not. And here the hacker has double challenge. So hacker may guess S, but if does not know key K, it cannot change the message. If hacker knows key but not S, again it cannot change. If hacker knows both, which is very difficult. So this is a little bit complicated, but this is more secure. So this is one example of application of hash codes. So I will end lecture here. I don't want to make longer videos. So in next lecture we'll go in deep details of hash function, what are its properties and its other applications also. Suppose digital signature is another application, we'll see that, but then we will try to study a couple of examples of simple hash functions, how they are actually designed, and then we will do message authentication codes, and that is pretty much sufficient for our unit 3, which is the message authentication code. And then the last part is I think that will be the easiest topic in the course. That is about firewalls, IP security, virtual private networks, and I mean that is completely non-mathematical. It will be like essay writing and some block diagrams, and I think we are into for the last stage of our course now, and I can say that we have pretty much covered not everything, but we have tasted what is called symmetric ciphers, then asymmetric ciphers, and in that we have done very important RSA. One thing we have done extra, which is not there in the syllabus but should be there, syllabus is not important, that's AES algorithm. We did that, but it is unfortunately not in the syllabus, but it is very important, it's very frequently used. Couple of things I have left, like Diffie-Hellman algorithm, but that you can study of your own, or if I find time I can have one video on that also. So I hope that in a couple of videos inshallah we'll be able to wind up the course. Thank you.